Okay, so welcome. My name is Buff Furman. I'm the instructor for Section 3 here of NE 195B. This is Senior Design Project 2, and our section is got 7 projects in it, and 4 will be sort of presenting as one project, as you'll hear more about. But it's all focused around the Spartan Superway, which is a solar-powered automated transportation system that we've been working on here at San Jose State for the last about 12 years. And all these teams have a lot to say about their specific project, but it's all about envisioning, demonstrating, developing technology for a new way of doing transportation in urban areas that's sustainable. So I'm going to turn it over to Michael to introduce his team and start off the presentation. So thank you very much for coming.
All right, so real quick, before we get into the meats and details of our project, I'm going to go over kind of a little bit of a refresher or an introduction to what this whole Superway is, essentially. And let me answer the question, why do we need the Spartan Superway? So let's start off with kind of the main issue that we're trying to tackle, and that is global warming is an issue that we just cannot ignore anymore, or we could not pass on anymore, or we cannot just hope that someone is going to step in to fix it. Because according to data, 2023 was the world's warmest year on record. So kind of the time for waiting is a little bit over now. There isn't really a superhero that's going to come and save us. So we need to take it upon ourselves to develop something that can combat this. And in terms of kind of how CO2 emissions are, we're not really doing much. So this is just a picture of 237 when it's pretty packed. And I'm sure if you drive a car, you know the feeling of lots of cars on the highway, and it's a lot of CO2 emissions. But, you know, driving the car is nice, it's very convenient, and that's kind of the problem there. The convenience of driving a car is still pretty significant. Well, there are remedies out there like the light rail, like BART, and other public transportation methods, and they are convenient and they don't emit as much CO2 as cars, but it can only do so much, and it can only fit so much, and it can only scale so much, which is also a problem. So just going through kind of the news and like Mercury News and, you know, all the news you pop up in San Jose and the Bay Area, there's been a lot of articles and information coming out that it's getting kind of harder and harder to scale public transportation. And certain public transportation services like BART have had a kind of a battle with the government in terms of getting more funding. And recently, BART is trying to expand. They're trying to expand 6 more miles than they currently are. And when we kind of look at the cost analysis of this, it doesn't really make any economical sense. So I'll tell you what I mean by that. If you go into that article and we read that 6-mile extension project for the rail line is expected to cost taxpayers how much? If you had to take a guess, well, the answer is $12.75 billion for 6 miles of added track onto BART. That is a crazy number. It's not even the worst part either. That is after they promised that they would cost only about $6 million to add 6 miles of track. So this is double what they promised, and now it's just ballooning. And you might ask yourself, really? Like, does it really cost $13 billion to add 6 miles of new track? And let me tell you kind of why that is. So, billions of dollars, months of labor, constant problems for just only 6 miles of track added? Is there a better way? So, kind of the reason why that is because they have to take a giant boring machine to dig underneath tunnel in the Bay Area. And the size of this machine is bigger than a 5-story building. And this is being developed in Germany, so it's got to be exported to the United States from here to the Bay Area. And this is an absolute monster size of a boring machine. And if I read correctly, it's actually one of the largest machines to kind of dig through dirt that's been ever made. And it's costing about, I want to say it's about $300 million to make this so far. You know, costs can always go up. So yes, is there a better way than to just dig through dirt and spend $13 billion to add 6 miles of track? well, why don't we just use an automated transport network to reduce labor costs, to reduce labor, to reduce costs, and to potentially reduce greenhouse gas emissions? And so what that kind of means is that instead of trying to go underground and dig through the dirt, why not just lift it up into the skies like we have here? So that's kind of the basis of what an automated transport network is we're not going to try to put it into the ground, we're trying to put it up into the sky, and we're trying to put people in these things called pod cars, or bogies is kind of the shorthand term that we're calling it. So the idea is that on this overhanging monorail type of system, you have these little bogies that go through the track and they fit maybe about 4 to 6 people inside of it. You tell, hey, I want to go from point A to point B. And then without a driver, this bogie will take you from point A to point B and anywhere you really need to go. So that's kind of the vision of what an automated transport network is. And the idea is that this is a constant 24/7 automated transit system. So you don't really need to rely on a driver to get to where you need to go. You could just rely on, hey, let me pull up my app, kind of like Uber. I want to go from point A to point B. Okay, let me schedule a ride. I'll go to a station, I'll hop on, and then I'll get there. So that is kind of the basic concept of what an ATN is. What Spartan Superways is an extension of that. It is, okay, we want to be an ATN network, but let's have an emphasis on reusing renewable energy to power this whole system up. So this is kind of concept art of what we want the Spartan Superways to be at its end product. And you can see it's just lots of solar energy, and we're going to utilize that to power the whole system together. And so rather than just tell you, okay, yeah, this will let you get to point A to point B, this will reduce greenhouse emissions, this will reduce cars off the road, let me show you what that looks like. So here's kind of just a general concept of what streets look like nowadays, where you just have multiple lanes, you have buses, you have these tiny little sidewalks, and then you have cars everywhere. The kind of vision that the Spartan Superway wants to do with an ATN network is to reduce the cars off the road and reduce CO2 emissions. So that would look like something like this. So if you notice from this picture, the density of the road has greatly decreased, and we also have overhanging ATN networks going across, and we have more sidewalk space. So you don't really have to worry about getting, I don't know, San Jose. So you don't really have to worry about as many cars because there's less room for cars to drive, and it's more accessible to walking. And so if we want to take that even one step further, we can actually. So here we just completely cut off an entire road and make that completely walkable space to go on. And we could get creative with that. You could have pop-up shops there. You can have playgrounds there, whatnot. The point is we're not only reducing cars, but we're also increasing the usage of our land here. So it's not just cars. And if you really want to get ambitious, we could take that to a whole nother level, and we could just get rid of the other road too. So what you have here is what looks like half a park, and then half just urban walking space. And the point is, you don't see any cars here anymore. So it's this dream, it's a lot nicer. I don't really like seeing too many cars around, and I would love to have something like this. But this isn't really feasible right now because we just have too many cars on the road because we don't really have enough transport solutions to get us from point A to point B. So that is sort of one of the problems that the Spartan Superway is trying to run. But that is an ambitious idea, I will admit. But we can't just go from point A to point B, and we can't just say, okay, we'll have it done by tomorrow. In order to get there, we have to, like a baby, we have to take little baby steps to get there. Before we can run, we have to first learn how to walk. In order to do that, that's what we're here today for. We have our projects right here ready to demonstrate and showcase to you all today. We're showing you the baby steps to getting to that end goal. And so what I have right here are just some preview concept art and early footage of some of our demonstrations and projects from earlier this year. And yeah, this is essentially our baby steps, baby footage when our projects were just maybe 1-2 months old. So So there's that. That is kind of the introduction to what the Spartan Superway is. I gave you a little taste of what an ATN is. Now we're just gonna show you how we're gonna put that together in these small scale demonstrations that we have prepared for you today. And the first step to doing that is with these little bogies right here. So if you know, these bogies need power. So how do these bogies run? How are we gonna make them run? How long do they charge? These are questions that we have to address. And so with our first team, we have the Vehicle Energy Storage and Charging team, and that is us right here. So we'll take you through how we're able to manage to power this bogie, kind of the cool stuff that comes along with it, and more plans to come. All right, so to introduce our team, hi, my name is Michael.
I'm Anton. I'm Roman.
I'm Naila.
I'm Patrick.
All right, and we are the Energy Storage and Charging team. So to kind of give you more on the project background and information about our project, I'm gonna hand it off to Naila to talk a little bit more about that.
Thank you, Michael. I would just like everyone to give Michael a round of applause, please. Thank you. Okay, so our project is, so what is our project about versus like the overall Superway? Focusing in on our project is the Energy Charge and Storage team, and we decided to develop an energy charge and storage system which utilizes batteries and supercapacitors to power the motor on the bogie, and this is, or the vehicle, which is also called a bogie, which is right here. So the hybrid energy storage system is crucial for the Spartan Superway because it continuously supplies power to keep the bogie operational over long distances. So as Michael mentioned earlier, the bogie has the capability to go from point A to point B. It's not like a bus where there's different stops, and because different people need to get off at different stops. And for BART, it's like mandatory to stop at each stop. So the bogie the Spartan Superway would definitely like shorten that that amount of time it takes to get to your destination. So these purple circles here are like the possible stops of the bogie, but the yellow represents a path from point A to point B because it doesn't have to stop depending on where you're going as a passenger. And to put things into perspective, if I'm a student, so sometimes I like to go to the mall on the weekend, so or watch a movie. So if I want to get to the movie theaters by my car, it would take 13 minutes. But if we have the Superway, I would be able to use my phone and call the use the app and go to the station and be able to catch the Spartan Superway, and that would probably cut the time in half. So I wouldn't be able to, I wouldn't have to worry about driving a car, and I wouldn't have to worry about traffic, and I would be able to get to the movies on time, and also not have to worry about finding a place to park, and also you're saving the environment at the same time and not using greenhouse gases. So that's really beneficial, and I'm gonna pass it to Patrick to explain our project objectives and design specifications.
Okay, thank you, Naila. So I'm going to talk about the objective and design specification. So our objective is build a stable, fast charging energy storage with large capacity for the vehicle. And this is just some pictures for the final product. So in order to supply enough power and receiving the power from the solar panel, we decide to implement the hybrid system using the supercapacitor and a battery. The reason that is supercapacitor and lithium-ion battery are two types of different energy storage. supercapacitor has the characteristic of fast charging, but with low stored energy. The lithium-ion battery has the slow charging time, but and it stores a lot of energy. So what we're trying to do here is combining the advantage of each type of energy storage and basically make it possible. So we developed and tested the charging system with a lot of iteration. For this semester, we have at least 6 iteration, different kinds of wiring and testing, and this is the final product of our circuits. And so far, we achieved most of our functional specification. Being one of them is we are able to output the voltage to the motor with 9 volts. And you may be wondering why there's a check mark and a question mark. That's because we weren't able to measure the current when the motor is running yet. We try to measure it, but during the process last week earlier, we kind of blew up one of our circuits, and we decided to hold it back. But instead of measuring the actual current from the motor, we tested with a smaller motor that we were drawing 0.6 ampere as a backup plan. And for a supercapacitor, we were able to charge it under a minute with the maximum voltage for the supercapacitor and its working voltage rate with 3.0 amperes with charging current, and we were able to charge the Pi sugar with 5 volt, which is required by the Pi sugar. And I'm gonna hand it to Anton to talk about literature review and design approach.
Thank you, Patrick. Okay, so when it comes time to start working towards completing a complex engineering challenge, it's often a really good exercise to look at how that technology is currently being implemented in the world. So there's no real need to reinvent the wheel in a lot of the time. So if you can take a look at what other organizations or other technologies, how they're implementing maybe a piece of what you were trying to accomplish, often very beneficial. So in doing so, we started researching the history of ATNs and why they came to be, also the kind of current state of ATN development throughout the world. And we found that the first ever ATN that was ever put into working condition and is still actually operational to this day is the Morgantown ATN. And it was envisioned as a way for students in West Virginia University to kind of go throughout the campus and also connect, I believe, a satellite campus to the main campus or just something along those lines. So essentially, this system ended up working really well, and it's still in use today, it's still operational. And it's kind of become the blueprint for what we think of when we think of ATNs, when we think of these autonomous transit networks. So we basically then started looking over the previous groups, the previous Spartan Superway charging team groups, because we wanted to understand what they had done so far, what their kind of design process was. And we found it really helpful because we found that the team previous to us had managed to get the supercapacitor side to work, but they had challenges with the hybrid system. So the hybrid system became our main goal because as my team members said earlier, there are benefits to mixing and matching, I guess creating a hybrid system of both the supercapacitor and battery that take the desirable characteristics of each energy storage medium and combines them in order to make a system that is able to charge quickly, efficiently, and safely. So that's another thing. So we first developed, this is kind of our first iteration of the design. So right here we have I'll just use my mouse. So here we have a kind of power supply. This is our original kind of power supply that we were using to power the whole system off of. This was essentially emulating what the input power would be from the solar charging team. But we wanted to be able to test stuff on our own without relying on it, so we created a contingency that we would use this just to kind of test our circuit, make sure all the voltages and currents were up to spec and what we needed from our output. So this had a lot of issues, as first prototypes often do. You know, walk in and you think, oh, it's all gonna work perfectly. It didn't at all. So we had a lot of issues with this, but it was a really valuable experience. And it paved the way kind of for the direction that we wanted to approach the problem going forward. Again, literature review, looking over the body of work that was completed prior to our tackling this problem was beneficial and pretty much like essential to us actually having the end product that we finalized. Okay, I'm gonna pass it off to Naila, who's gonna talk about the codes and standards.
Okay, so codes and standards are really important to follow, especially when we're working on projects and we are dealing with electricity. And we used several, the system used several codes and standards. And as you can see here, this is IEEE, which means it stands for Institute of Electronics Engineers. Then here's the NFPA, the National Fire Protection Association. And then we also have ASME, which is the American Society of Mechanical Engineers. These are like relevant standards and codes to our project. I don't want to get into all of them. I feel like that's for our report, but this, just pointing out a few. So IEEE 1536, the standard is for the Rail Transit Vehicle Battery interface, and it was just recommending to use a proper battery holder and make sure that there's enough space so the battery can essentially breathe. We, in our previous design, we had electrical tape holding the leads to the battery, which was not good. And we eventually got a battery holder specifically for the 18650 battery. So that's one way we used like the codes and standards to improve our project. And then the other way was that to prevent like fires and electrical hazards, which was what like all the codes are basically for. We decided to implement the TP 4056 and the Pi Sugar because they both have like battery management systems embedded into them. And yeah, I'll pass it to Roman to talk more about our design.
The path to get to our final design was not easy, but we were able to get there in like 3 major steps. Our hybrid energy was developed, and despite numerous designs and tests, the first step we took was messing around with the supercaps, using a variable power supply to get to where to get values that are safe to work with, but also that the solar team can provide to us. Once we figured out these values and ranges that we wanted to work within, we started developing designs to keep our battery safe. Supercaps tend to have a high discharge rate, which can be dangerous if we connect them directly to the battery, which is why we ended up going with a battery charging module, which is a TP, which prevents the high currents and high voltages of the battery from the supercaps to charge the battery. With the TP chip, we were able to output a consistent voltage, but it lacked enough power to run the actual motor. We were able to charge the supercaps at around 5 volts, which would then 5 volts and then 2 amps. This would then run through the TP chip to a boost converter to boost it up to where the pi sugar is, which then runs the motor. Because we weren't able to provide the required current to run the motor, we doubled our design, stacked it on top so it's like a parallel. This didn't increase the voltage, but it did increase the current to where we could run the bogie. Our final design is able to provide enough power and run the system, and our measured output we got was around 9 volts at 0.6 amps. And here's how it looks in person, and here's a video of it working. Now I'll pass it on to Michael for future suggestions.
Before that, I just want to emphasize that the power rating that we measured was at essentially an idle torque. So under load, we would be able to produce or supply more power to the motor. So that reading, we were unable to get a current reading while it was running in the bogie, but it basically overcame the torque and the inertia of the motor. We were able to provide enough power, essentially.
Yeah. So, given our project, there's a lot of electrical intricacies and knowledge that we had to learn along the way, and came to a point where things were quite literally catching on fire. And from all that, we were able to verify that, yes, this is going to make this explode. Let's not do that. Let's add something that's safer and will not cause it to explode. So, major source of our work was trial and error, making sure that, hey, this is safe. Can this run the bogie without catching on fire? We're confident that it will not catch on fire. So, given that, our project works. But it's always a question that every engineer should ask themselves: can it be better? Absolutely, everything could be better. And with our system, if you kind of piece it together, we have a buffer system that acts in between the battery and the supercapacitors together. And that buffer system could be more efficient. It could take a little bit longer to charge these two batteries. We also have it in the parallel configuration. We also have a lot of boost converters here. There could be some future work done to cut that down to make things more efficient. And maybe even develop our own TP chip solution that can be more optimized to the outputs that we need. So of course, it could be better. And that's specifically when I'm talking about the buffer, I'm talking about this region. So this is the output, this is the input. And with all that come together, what we get is a bogie system that can glide through a third rail system and touch the contact points and instantly get charged. So if we were to just do purely batteries, we'll be dealing with this situation. If you've ever been in a Costco gas station line and you just have to sit there and wait till it's your turn to get ready to charge. So let's not do that. Instead, why don't we just act like where the gas station is, act like it's a finish line. Like you're a race car and you're going through the finish line, and somehow when you go through that finish line, you're getting charged. So you don't have to really stop and wait to fill up your car. What we're doing is you go, and as you're moving, you're getting charged. So that's a very big emphasis on our part. Let me say it again. So when you're moving through a charging station, you will receive charging and you will not stop. So that's kind of the magic and the hassle that we've been working on. And kind of the end goal is that what I just mentioned in a little diagram here. We have all of these autonomous pod cars moving, and then if your battery gets a little low, just go through the charging station and then lap through that third rail, and then you'll get charged. And you'll and then you'll just go back into the traffic. So it's very nice convenience to not have to wait and charge a battery. And so kind of before we conclude this presentation, let's ask ourselves again, why are we here? Why are we in this building? Why are you guys watching us? Why does the Spartan Superway exist in the first place? Because we have to ask ourselves, well, with the issue of global warming, if we don't act now, who will? So here we are. So that concludes our presentation, and I'm sure there's many questions, so ask away.
Any questions for the team? Anybody have a question? Okay, so where can they see your work after we conclude our session today?
Oh, sure. So we have a little back room with our graveyard of dead equipment and also our current prototypes stored in here. We've also had some work on these bogies. But if you want to see a demonstration, we should be more than happy to get something. Yeah.
Okay.
So you'll get to see all the lights turn on, and hopefully, not hopefully, I don't want to insinuate that there will be a hazard, but
I mean, Cal Fire's out there. So.
yeah. So we've ironed that out. So it should be pretty safe.
Okay.
Is this one we're gonna see, or is it over there?
It's both.
Both. Okay.